Good morning, and welcome to the second of two videos. No, I lied. Three videos on Chapter 6, um, which is all about z-scores and how they are used in statistical analyses. All right. So remember from the previous video that z-scores are simply the number of standard deviations that a particular raw score is from the mean. All right, and so what we're going to do in this video is begin to learn how to interpret z-scores using the z-distribution. Now, again, remember from the previous video that the z-distribution is simply a normal distribution that shows the standard deviations away from the mean. All right, and so we're going to look at a few normal curves. All right, with scores and with raw scores and with z-scores, and kind of look at how the relationship exists between the two things. So a z-distribution is the distribution produced by transforming all the raw scores in the data set into z-scores. Now, let's think about what that does. All right. If you take a normal distribution and you've got this normal distribution and you then convert every raw score into a z-score, what does the shape of the z-distribution actually look like? Well, hopefully, if you think about it, right, because every score is going to be at the same location on the normal curve, the z-distribution and the raw score distribution will look exactly the same, okay? And so you're not changing the shape of the curve. You're not even changing the meaning of the curve. You're just changing the way that the curve is illustrated numerically. Rather than have the raw scores on the x-axis, you'll have the z-scores instead. And so then a normal z-distribution will simply have a range of x-axis values from -3 to +3, right? Just slightly below -3 and just slightly above +3. But still, from -3 to 3 will be the range on that x-axis. So a z-distribution is simply the distribution produced by transforming all raw scores into the data, in the data into z-scores. So what do I mean by this? Well, let's have a look at our attractiveness scale that we looked at in the previous video. All right, here we have an attractiveness rating that ranges somewhere between 0 and 100. All right, the mean score here is 60, and we have three individuals, Binky, Biff, and Slug, who fall at different locations along this distribution. Slug has a raw score of 35, which is very ugly, apparently. Binky has a raw score of 65, which is better than average, but not much. And then Biff apparently is quite the stud. He's got an attractiveness score of 90. Now, notice up here at the very top, we've got the standard deviation listed. And so we know that the mean of this distribution is 60, but the standard deviation is 10. So what does that mean? Well, one standard deviation below the mean would be 50, right? Because the mean is 60, minus 10 is 50. And that puts us right here, okay? And so a raw score of 50, because it's one standard deviation below the mean, has a z-score value of -1. Now, on the other hand, if we go one standard deviation above the mean, then we have a score of 70, right? Because 60 plus 10 is 70, all right? And so that means that a raw score of 70 would correlate with a z-score of +1. All right, now, here is one standard deviation. Here is two standard deviations. Here is 3 standard deviations above the mean. Now, And the same thing can be done on this side. Here's one standard deviation below the mean, two standard deviations below the mean, and finally 3 standard deviations below the mean. Okay. Now, what does that mean? Well, that means that slug has a raw score of 35, which is a z-score of -2.5. Right. 35 is 2.5 standard deviations below the mean. Binky has a z-score of positive 0.5. Right, because he's half of a standard deviation above the mean. So a raw score of 65 correlates with a z-score of positive 0.5. And finally, Biff has a z-score of positive 3 because a raw score of 90 is 3 standard deviations above the mean, and therefore his z-score is positive 3. Okay, so the other thing that you should notice from that slide is that the z distribution had the same shape as the raw score distribution. There were no differences in those two shapes, right? And matter of fact, you only saw one curve on that thing. Why? Because the raw score distribution and the z-score distribution look exactly the same. Okay. The differences are, I should say, are that the mean of any z distribution is 0, right? That's where we're going to start. Right in the center is the 0 mark, and then anywhere to the left of that will be a negative z-score, and anywhere to the right of that will be a positive z-score. Now, interestingly enough, because a z-score is essentially given in standard deviations, that means that the standard deviation of a z distribution is 1. Isn't that convenient? What can we do with that? Well, you're going to have to wait to video number 3 in order to find out the answer of that. But for now, just keep in mind that the z distribution looks the same as the raw score distribution. The mean of a z distribution is 0, and the standard deviation of a z distribution is 1. All right. Okay. Now, let's have a look at 2 different z distributions that are shown on the same set of axes. All right. These are scores of a high school class in both statistics and in English. All right. So the same kids are taking English as are taking this statistics course. Now, the raw scores are written on the lower 2 lines of the x-axis, right? So in statistics, they range from 0 to 45, and in English, they range from 0 to 70. Okay. Now, you can see that the shape of the 2 distributions is pretty similar, right? They're both normally distributed. And so what we do is we make the mean 0. Okay. Even though the mean in statistics is 30 and the mean in English is 40, all right, we're going to make 0 the mean value for both z distributions. Now, what that does is it allows us to compare the 2 classes in terms of their z-scores. Now, in statistics, the standard deviation is 5. All right, so 1 standard deviation below the mean is 25, 2 standard deviations below the mean is 20, and 3 standard deviations below the mean is 15. The same thing on the right side, we go up by 5, 35, 40, and 45 for a z-score of positive 3. Now, in English, on the other hand, the standard deviation is twice as great. It's 10. And so 1 standard deviation below the mean is a 30, 2 standard deviations below the mean is a 20, and 3 standard deviations below the mean is a 10. All right, 1 above is a 50, 2 above is 60, and 3 above is 70. Now, what this illustrates is that if you look at Millie's scores, for example, apparently Millie scored a 20, a raw score of 20 in statistics, and that put her at with at a z-score of -2. So it's 2 standard deviations below the mean. Okay, so she's not doing very well in statistics. All right. In English, she's 1 standard deviation below the mean. All right, which is not great, but it's better than she's doing in statistics. All right. Notice though that her scores in statistics, she has a raw score of 20, and in English, she has a raw score of 30. Okay. Now, Althea, on the other hand, seems to be a better student. All right. In English, she has a z-score of positive 0.5, so 1/2 of a standard deviation above the mean. Well, we know that the standard deviation in English is 10. Therefore, what is Althea's raw score? All right, well, half of 10 is 5, so 40 plus 5 is 45. So Althea's raw score in English is 45. Now, in statistics, her z-score is positive 1.6, so she's 1.6 standard deviations above the mean. Now, the standard deviation in statistics is 5, and so 5 times 1.6 is 8. And so therefore, what is her raw score in statistics? Well, it's going to be 30 plus 8, which is 38. Okay, so that's how you would use these z distributions. Okay. A couple more things we want to add to this discussion. All right, relative frequency is one of them. Relative frequency can be computed using the portion of the total area under the curve. All right, relative frequency can be computed using the proportion of the total area under the curve. All right, now, what does that mean? Well, in a couple of slides, I'll show you a picture of the normal distribution with the percentages of the area under the curve. So we'll get there in just a moment. But the relative frequency at a particular z-score will be the same for all normal z distributions. All right, doesn't matter what the raw score data looks like, as long as it's normal. The relative frequency of a particular z-score is the same in all normal distributions. Now, the standard normal curve is a perfect normal z distribution that serves as our model of any approximately normal z distribution. All right, because in reality, nothing's ever exactly perfect. Okay, but we're going to use the standard normal curve as a comparison to any z distribution that we want to look at, and we're going to use that to as a comparison for any normal, or at least approximately normal, z distribution. What do I mean by that? Well, here is a picture of the normal curve. All right, and this is shown with a z distribution. All right, so there's no raw data here. These are all just z-scores. And as we said earlier in the semester, 1 standard deviation above the mean is 34%. 2 standard deviations above the mean is another 13 or 14%. So we're up to almost 48%. And then 3 standard deviations above the mean is another 2%. And so we're up to almost really, really close to 50% of the data to the right side of the mean. And that's what you see here. All right, the same thing is true on the left side. You got 34% here, you got almost 14% here, and you got a little over 2% here. And again, this represents 50% of the scores are below the mean. Okay, so in terms of the z-scores, all right, what this means is that a z-score of -1 is 34.13% percent below the mean. Okay, and actually we're doing relative frequency, so 34.15 or 13% of the scores fall in that first standard deviation below the mean. Okay, Now, in terms of the relative frequency here, all right, for any approximately normal distribution, transform the raw scores to z-scores and use the standard normal curve to find the relative frequency of the scores. Okay, and we'll do an example of this in the third video, but we're getting there. Okay, we're getting there. All right, so for any approximately normal distribution, transform the raw scores to z-scores and use the standard normal curve to find the relative frequency of the scores. All right, how frequent are they? Now, another thing that we can do with this data is to calculate the percentile. All right, and that's kind of what I was getting to when we were looking at the curve a few slides ago. So the standard normal curve can also be used to determine a score's percentile. All right, for a given percentile, where we also know now. Don't know what happened here, but this is obviously X bar, and this is obviously the standard deviation, so mean and standard deviation. So if we know these two values, we can use the percentile to find the z-score and then compute the associated raw score using the formula that we talked about in the first video. All right, X equals z times the standard deviation plus the mean, okay, for the sample. Okay, so for a given percentile, where we also know the mean and the standard deviation, we can use the percentile to find the z-score and then compute the associated raw score using the formula that we learned before. Okay, now, what does this mean? Well, it means this. Let's say we go back to our attractiveness scale here, and we start with a new victim on this scale. And the victim's name is Elvis. Now, Elvis has a raw score on the attractiveness scale of 40. Okay. Now, we know that the average score is a 60 and that the standard deviation is 50. So, a raw score of 40 corresponds with a z-score of -2. Okay, a -2. So, what does that mean? Well, at two standard deviations below the mean, there's only 2.28% of the population, or the sample in this case, that are below that score. All right, and that's what this number here illustrates. All right, 0.0228 or 2.28% of the scores are below Elvis. All right, that means that Elvis is in the third percentile. He's between 2 and 3% on this. All right, so Elvis is a butt ugly dude. Okay, but that's what this means. And so we can use raw scores, percentiles, relative frequencies, and z-scores interchangeably, and we can use them to calculate any of the others. Okay, so that, my friends, is the end of video number 2 of 3 for chapter 6, and I hope you learned something.